Hello, everybody. My name is Andrei Cotai, and together with my colleague Tiberiu Boros, we're going to have a discussion regarding machine learning and how we can use it in our day-to-day work, for good or for evil.
So we are going to begin with a short disclaimer. Adobe invests a lot of effort in developing machine learning algorithms that aim at improving customer experience. However, we do not represent our employer or any of the ongoing projects.
And that's especially because what we were sending today is not the most correct message. Anyway, regarding this presentation, the main question, do we trust machine learning? They don't want to answer, Tiberiu. You can go ahead.
Okay, so I think we do, because every day we consume technologies that are enabled by machine learning. So as all of you know, big online platforms use machine learning to create that experience that we already take for granted. And this is just the beginning. So are you familiar with generative models? Anyone? Anyone? That's great. So there are a special type of machine learning algorithm which is designed to produce samples. So we have a couple of examples here. We have handwriting, we have audio. So we also have you seen the deepfake videos? That's nice, okay. So that's pretty much the whole deal. So I'm mentioning these models because we are going to use them in today's presentation.
Okay, so we actually gave it a lot of thought what we want to deliver today through this presentation, how complicated to make it, or how boring for that matter. So we actually decided to make it pretty straightforward, simple, and applicable. So we would like at the end of this presentation, everybody in the room to be able to train their own neural network. For what purpose? It's your business. So we are going to touch some subjects like machine learning and especially neural networks. We are going to show you how you can actually train a neural network, how you can execute it in different environments, and some small chatter about JavaScript, reverse engineering, and some anti-forensic basic concepts. Now, before going further with the presentation, I would just like to mention that this POC, or actually this idea, can be translated into any programming language that actually works with machine learning frameworks. Now, and I presume that most of them are able to do that today, but why JavaScript? Well, JavaScript is actually everywhere. I'm pretty sure like most of the pages you are going to visit in one day, they are going to contain a JavaScript piece of block there. There is JavaScript code on your system. There are JavaScript files on your system. There are native interpreters who actually can execute those files. And lately, we actually saw a lot of desktop applications that are built on JavaScript frameworks, like the Electron one. So I'm pretty sure there are a couple of icons that most of you guys are actually using daily. So that means there is a lot of JavaScript code that we trust. And that might mean actually a lot of JavaScript bad coding that we might be able to exploit. Now, I'm pretty sure everybody in the room is pretty familiar with most of the attack vectors regarding JavaScript. And those are because things like bad coding, vulnerable servers, fake services, or third-party compromises, like we saw the British Airways hack a couple of months ago. But what do attackers try to achieve through those vectors? Well, they're trying to do things like recon. They're trying to get as much information as possible about you. They're even going to use JavaScript pieces of function to scan your internal network and send the data back. Or maybe they just try to hijack your resources and do mining, click fraud, maybe sometimes just drop a little bit of malware on your system, or why not? Exploit your vulnerable web browser and run that beautiful shellcode there. But what do most of those pieces of code have in common? Well, most likely they are obfuscated. Obfuscation is not necessarily something bad. Lots of developers use it, and that's because you basically, when you visit a page, you're going to download the content locally. So that means you're going to have clear text access to the entire code there. So developers are going to try to copyright protect their code by obfuscation. So that means messing up with the variables, messing up with the logic, messing up with the strings there, trying to make this as unreadable as possible. But that's still statically probable. Probably you are going to be able to revert it to, not necessarily to its original code, because you can never know how that variable should be named, but you can have an understanding of what that code can be, it's doing there. Now, attackers are trying to do basically the same thing. not necessarily because they have concern regarding copyright protecting, but they're trying to blend in. They're trying to hide their presence or their intentions there. So what we are trying to do today is actually taking one step further and demonstrate that we can actually hide code, malicious code for that matter, in neural network, and there is no mathematical way to actually revert the code back. And also, you actually are going to see that's pretty hard to do, even dynamically debug that code, even in a debugger.
So because we are dealing with machine learning, we want to raise the attention to one question which we have in mind for today's presentation. That is, machine learning is about encoding, encryption, or compression of data. So basically, everything will orbit around that in what follows. So there are many recipes for building generative models. I mean, you can train a feed for a neural network in a certain way to make it generate samples. You can use convolutional neural networks, or you can use recurrent neural networks, which are my personal favorite. So on the left side, that is a schematic of a basic building block of which is called a long short-term memory network. It is designed for a special type of network, and the thing about it is that it learns what it needs to remember. So it's a type of kind of a fuzzy memory, which is controlled by a couple of gates. So we have the input gate, or what it needs to remember, the update gate, or what it needs to, when it needs to remember, the forget gate, what it needs to forget, and also the output gate, which stands for what it will let others know it remembers. So we actually use this network by overfitting it. So what is overfitting? Well, machine learning algorithms like lots of data, so they can extract patterns from it. But imagine that you have a really small training set, and you have a network that's supposed to label images, and you show it, okay, this is a cat, this is another cat, this is also a cat and a cat. When you show it a different picture from the office, maybe it will actually choose to see cats. So this is one definition of what overfitting means. The other one is that the network is able to perfectly reproduce the training set, but it generalizes really poorly. And we are actually counting on this. There are plenty of machine learning frameworks out there. You can see a whole bunch of them, which we quickly Googled. We use Brain.js, which is an awesome platform, but actually it was a random choice for us because it worked at that moment.
Okay, so now let us combine our favorite technologies, the JavaScript, machine learning, and HTML, and see what we actually can achieve. But before that, I'm pretty sure this is a question you heard a lot of times in movies or at work or when your boss is asking you something. But anyway, what is the definition of insanity? So if you do a Google search for that, you're going to see that the definition is doing the same thing over and over again and expecting different results. And that's what actually we are going to do today. We're going to run the same POC 4 times, but we are going to have different results. Now, there's a catch, and we're lying here a little. Even though it's actually the same JavaScript code, the neural network is different. So the things we are going to put in our neural network are different, and they are going to execute different stuff. So let's get with the first demo, and this is the most important one. Why is it important? It's because it's the full code that you need in actually to train a neural network for our case. So let's dig into it. Now, Tiberiu already mentioned that we are going to use the Brain.js library for this. And Brain.js is a really cool library, and they have an awesome Git page for this. And if you go to their Git page, you're going to see a couple of really, really nice examples. So you don't really need to know machine learning in order to use their toolkit. They have examples for that. So in our case, we are actually going to download locally the library, and we are going to load it from there, and that's how we're actually going to use this framework. Now, in order to train a neural network, or a machine learning object for that matter, you need 3 elements. You need a machine learning object, you need a training function, and you need training data. So in our case, that is the training data, and Tiberiu already mentioned that machine learning really like patterns, like they don't want to reproduce, they want to learn stuff, and they want to do as best as they can. And in order for that, they need lots and lots of data. If we're speaking about neural networks, we might actually need millions of entries there. Well, in our case, we have just one entry, which is pretty simple. And let's take a look at it. We have 2 keys inside our entry. We have input and output. So input means what I'm going to feed the neural network, and output means what I'm expecting the neural network to respond with. In our case, there is no pattern between those two things. Let's be honest. We have a string which is 1, and we have a huge string which is apparently JavaScript. So there is no way our neural network is going to be able to learn any pattern from this small amount of code. So as I mentioned, next we need the machine learning object, and we're going to create that by using the brain.js. We're going to create a neural network, and it actually writes there an LSTM kind of network. And then we are going to train the neural network, and we are going to do that by using the built-in training function that the brain.js has. So the training function requires 2 input parameters. It requires the training data, which we already covered, and it requires the number of iteration. That means how many times should the training function go through the data until it's going to learn whatever it has to learn. So in our case, having a really small amount of training data and lots of iteration, that's actually going to achieve overfitting, which Tiberiu already mentioned. Now, for our code here, we're going to use the built-in script function to JSON, and we're going to convert the just generated neural network into a JSON configuration, and then we're going to write it to disk so we can move it in another place. And in order to run the neural network, you actually need a function that's going to do that. In our case, the function is called run. It's pretty straightforward, and run takes as an input parameter the input that you are going to feed the neural network. So in our case, the training data contains the input 1, so the neural network should perfectly reproduce that output. But if you are going to enter something different, something it hasn't learned, it's going to generate total gibberish because it thinks it learned a pattern, but has no idea what it's going to do there. So it's still going to generate something, but most likely that thing is not going to execute. Anyway, in the meanwhile, we actually trained our neural network. And if you're going to take a look, there were 1,000 executions, and it perfectly reproduced my input. Now, just a second to look at the string we have there. So it's a JavaScript piece of string. I'm declaring a function called mjabo, because that's how a great programmer I am, and all my friends know how I like to name my variables. And in the function, I'm declaring a variable called br. I'm pretty sure BR stands for browser initially when I thought of this. And it's getting an information from the navigator. And after that, it's calling an alert function that should make a pop-up and tell me you are using BR. So pretty simple, is it?
Okay, so if we actually look at what the network has stored on disk, you'll see that we have a couple of hyperparameters which describe the network, such as the hidden layer sizes, the input size, the output size, some luggage which we can throw away, such as the learning rate on which the network was trained on, the decay, clip rate, and so on. We have one second.
Yeah, my bad. I forgot to press the key.
Yeah. So we are going to have a dictionary of symbols which are used to translate from the network's output to whatever our data looks like, right here on the bottom side of the screen. There are the typical characters in the English alphabet, plus a couple of special characters which are used by the JavaScript functions. And we also have the weights which make the magic happen. So these weights are used by the gates themselves, which you saw on the previous slide, and they are used to project or transform the input data into something the network can actually use. So they are trained, they are computed using something called convex optimization or backpropagation with gradient descent. And I don't think there is any way of actually telling from how the weights look what the network has actually learned or what is it going to do.
Okay, so I promised you that we're going to execute this from the browser. So let's build our HTML script. We are going to need the machine learning library. And this time, we're not going to take it from the local disk. We are actually going directly to their Git repository, which I mentioned already. It's pretty awesome. And we are going to dynamically load it from there. So everything is on the fly, right? After that, we're going to define a variable. The variable, it's actually going to contain that huge string with Tiberiu just displayed that contains some information regarding the network, the character table, and all the floating numbers, all the weights. So next, as before, we're going to define a machine learning object, and we're going to use the Brain.js library for that. And then instead of training the neural network, we're going to take this huge string there, which is actually a JSON, and we're going to put it inside the machine learning object we just created. In the end, we're going to execute the neural network as we've done before using the run function. And after that, we're going to use an eval to actually execute the output and see what it does. So can anybody tell me what's wrong with this HTML page? Like what's definitely triggering your spider sense of security awareness? You guys are just shy. So eval, everybody knows that eval has been misused so many times in achieving the malicious stuff. But just as a takeaway, bear in mind that there are quite a couple of other functions that are doing basically the same thing. Maybe not as easy to implement as eval, but in the end, they're going to achieve the same thing, dynamic code execution in the page. So we just create our page. It's pretty simple. We are going to execute it. And as you guys expected, we're going to have an alert that's going to tell me to use Mozilla, even though I'm actually using a Chrome page. But we'll come back to that.
So let's go even further and maybe enhance our network by writing some more code. This time what we're going to do, we are going to make the network respond in some way when it sees one input, and in a different way when it sees a different input. So this is a really good method of actually hiding behavior because it's called conditioning. I don't know if that's relevant for now. So in the first part of the code, we actually set the same variable, which is browser, with the application code name, and we also load an URL, which points to an endpoint that displays the public IP address of the client. Also, in the first code, we launch the execution of the network again to generate the second code, which then makes a function which will actually will make the request and display a message. And because they are in the same DOM, they will actually have access to the same variables which we defined in the first execution.
Okay.
So we are going to run it, and any minute now?
We are running it.
Okay.
Yeah, we have a public
there's
IP.
the public IP address.
Awesome. And if you're going to look at the source code of the page, you're going to see it's basically the same code, just a different machine learning object with a lot of float numbers. Anyway, so we saw that we can add more code to our neural network and don't have to change our HTML page because we made the network call itself at the end of the execution of the first line. So we have random code execution, we have get request. Let us actually add a post request so you can actually move towards a more malicious spectrum. So in our case, the most interesting part of this code is actually the last input, the input called post. So that's the key I'm going to execute the neural network with. And the output, if you look at it, it's actually a function. It's called send data. So I'm not the most clever attacker ever. But my send data function is actually going to make a post request toward the random IP, which I just killed last night. And is going to send the content of the variable data to that IP. Now, the cool part is, if you look at my first input there, I'm starting the execution of the neural network with making another eval to the last part of code. So when I'm going to execute this part of the code, this function is going to be locally accessible in the memory of the browser. So I don't have to call the neural network again and again and again. I just loaded a piece of code in the memory which I can reuse it. So let us go through the data. It's basically the same data as before. As I said, I'm going to load the function send data by calling the neural network. Again, the magic URL. And we're going to make a jump from the first branch to the second branch. Remember, in the HTML page, that's just one eval function. Now, going in the second input, I'm going to have my favorite variable, again, br. And then I'm going to call the send data function, which I just declared in the first input. And after that, I'm going to do the same executions as before. So my page is going to behave exactly the same as we saw before. Oh, sorry, it jumped there. Funny. Actually, I'm missing one slide. Anyway, now let us actually look at the C2 server because apparently this is still here. So my C2 server is actually a PHP page and I'm going to listen for all the connections. So when the machine learning algorithm is going to call it, it's going to send a request here. And the page is pretty simple. It's just going to write the content of the file to a file. So in our case, this is the file. And we're going to execute the network. And voila, I just received that beautiful BR variable Mozilla to my code here. So it's pretty simple.
So basically, in order to get a better picture of what the code does in this type of scenarios, a good idea is to debug the code. So we can do that really easily by opening the Chrome Developer Console. And we are going to set two breakpoints, one before the execution of the network, another one after the execution of the network, to actually look a little bit at how the memory looks, how the variables are set, and so on. So wait for it.
Breakpoints. A console log. Run it.
Okay, so right now, we only have, except from the standard variables, we only have one object in memory, which is the network itself. It's the LSTM we defined earlier. It has its parameters, its weight, and so on. And we're going to jump after the execution. And now we're going to get more variables here, such as the browser, the URL, which gets the public IP address, and of course the send data function, which we defined earlier. So these are a lot of artifacts which we created just by launching the network. So again, if we go to the network tab, we're going to see all the requests it made. So it loaded some pretty standard stuff, such as the HTML itself, the browser component for the machine learning library, jQuery. It also made a call to the public IP address endpoint. And the funny thing is that it made a post to some weird looking IP address, which is written in clear. We also can look at the post data, and we'll see that the payload was Mozilla. So yeah, that's a lot of things to work on.
So now we actually can see the page. And when we execute it, as we saw before, it's actually going to return that beautiful alert that's telling my IP. But in the meantime, it's actually made also a connection to my third-party IP there. So as we saw, the simple execution of that piece of code actually generated quite a lot of artifacts. So maybe too many artifacts, maybe it's not, an investigator doesn't need any more to deep in the code because he's going to understand what's there. And let's be honest, the send data function, it's always something that will trigger attention. So let's think what we actually can do for our code to make it better, to make it attract less attention. So maybe we could implement some best coding practices there. And the last call our neural network is going to make, it's actually going to unset or delete all the variables, which we should do regular basis, not only for this code. And instead of sending data to that public strange IP or a strange domain, maybe you can with some cover channels. So maybe there is a way we can actually leverage some cover channels directly from the neural network. And the last thing, you have to be intelligent. I mean, you can add as much code as you want. It's your decision how you're going to make all the transition between the branches and how you can hide your code. So now just think of a couple of examples. You can actually learn your neural network with 100 lines of code and make 4 different execution branches. So when an investigator is going to look, he will never know exactly the full code that's there. He will have no way actually of reverting the code. He's going to investigate one branch and one branch only. Or maybe a practical example, take 10 user agents, browser user agent, put it in machine learning in a neural network, and make the neural network to generate malicious code only for one of them. So it's going to be really hard for the investigator to actually determine what is the machine learning doing, what is the neural network going to put there, if he's not going to actually brute force the neural network with all known user agents until he will get to the one that's actually going to have the malicious code. And maybe that's the way you can actually exploit a browser. Now, a last POC. So this is my Slack room, and as you can see here, I'm pretty lonely. I only have a bot there that will keep me company. So I'm going to make a neural network that's actually going to resolve that problem for me, my loneliness issues. So I'm going to execute the page. And this time I'm going to have an alert with my user agent, so I took it to the next level there. And if I'm going back in Slack, well, guess what? My browser just sent me a Slack message via the user agent. Like, isn't Slack a great tool? Like, you can do so many stuff with it. I personally love it. So let us now take exactly the same approach that Tiberiu did and look at this specific neural network again. So we're going to press F12 and use the Chrome debugger, which is an awesome tool. F12, I said. Okay, so I'm going at the source, going to set the breakpoints again, before and after the execution of the neural network. We're going to execute the neural network, and you're going to see we're basically going to have the same variables there, like the previous time. The only variable we actually have defined is the L, which is actually a machine learning object. Now, let us execute the page, the alert, and you're going to see now that we actually have a lot of variables there. No, we have only one variable that was created this time. It's the send data function, which this time is undefined, so you have no idea of the content of what the send data function is doing there. Maybe I could have named it otherwise. Maybe I could have named it login as Tiberium recommended, so it would have been even more obfuscated. But that's the cool part. Like the last call I did in my neural network was actually to delete or unset all the variables. So in dynamic execution, after the executing of the neural network, you're not going to see. Okay, let's go at the network tab, and this time we have the same things like logging the page, loading the machine learning library, jQuery because you use it for the post, and this interesting post here that we have towards Slack. So I just leverage Slack to send a message, a random message from my browser to my channel by Slack infrastructure. So should I ask you how many of you guys actually are blacklisting Slack in your infrastructure? I know we aren't. We're using it on a daily basis. So this is really nice. Like that's what I mean by cover channels, using some totally legit infrastructure like Slack to send the data there. And the cool part there, what I really like regarding the Chrome debugger is the fact that everything is clear text, my tokens, my headers, my everything. And that's because Chrome actually runs, the debugger in Chrome runs at level 7 in a SOC model, or level application from a TCP IP point of view. So that means I'm going to be displayed the entire content in clear text before it's actually encrypted and sent over the wire. And and Chrome is actually a really powerful tool from this point of view. And if you think of Wireshark, you cannot do that in Wireshark. Everything is going to be encrypted. So basically, you're actually going to need the public and the private key only to decrypt the code to see exactly what was sent there. So I guess those are our POC. I'm not sure if you guys saw, but HBO actually has it on display now, so I got inspired from there. The main takeaway is that you can do it yourself, and it's pretty easy. And this POC was made on JavaScript, but this technique can be applied in any programming language. You can use it in Python, you can use it in C. So imagine that you're going to make a malware that's going to call its code from a neural network. And when you're doing the classic reverse engineering of a malware, maybe you're going to put in a debugger, maybe everything is going to be in clear text, or you actually have to unpack your malware. So it's going to be really fun actually to reverse engineer that piece of malware. First of all, because you can have as many branches as you want. So it's not as fail. Okay, so you can have a branch. You can have a branch from Windows 16, you can have a branch from Windows 10, you can have a branch from Windows 7, 32 or 64 bytes. An investigator will never know exactly the code there, because once you're jumping on a branch, he's going to be, the other code will be invisible there. And he's never going to have any idea of the full capabilities of the malware. So that's just a problem. You're working? Yeah, don't worry. So that was our POC. You guys have any questions?
Thank you very much. We apologize for the technical problems. We're trying to figure out what's happening. Meanwhile, let's take some questions. We have our goodies as usual, and we have a question in the second row.
Is the main issue about training neural networks when you train them with user input? Or what is the main attack?
No, so the main idea is actually that you can try malicious code in the neural network. And for example, if you're going to scan that page, you have no idea what the neural network object is going to do, because there is no way statically to revert. So you can have whatever you want inside the neural network, and there is no way to actually extract it without actually inputting the correct key.
maybe I understand the question differently. I mean, you could actually, what you could do is train the network to respond to user input in a certain way that will generate malicious code at some point. I mean, maybe some, yeah?
It's a certain trigger.
Yeah, maybe.
We have some questions in the back there. Actually, they were first, the two hands to the far right, as we stand in front of you, so to your left.
First of all, thank you for so interesting presentation. I don't deal with artificial intelligence, but I have the question. So, the algorithm repeated your actions. What you did, it repeated it. And it reminded me the activity of the programs such Microsoft Office, Photoshop, the macros, where you record the macros, yes, and afterwards it repeats it. So as I understand, there is no any artificial intelligence, and or there is, and I don't know what is the difference.
Well, basically think that you could train it to maybe generate music and malicious code at some point, so I don't think you can actually do that with a macro unless you have, I mean, there are lots of use cases which cannot be covered by just deterministic execution of code. That's it.
So macros is not artificial intelligence, yes?
I don't think so.
Okay, thank you.
Thank you. We had a question in the back. Yes, the next row.
Hi. Actually, I have two questions. Maybe you don't choose. So, is the source code available anywhere, like of the samples that you actually did?
Not yet. That's because there were a couple of things in my private Slack key and a couple of my IPs. But if you go on the Brain.js GitHub, you're going to basically see exactly the same code, just different implementations.
Second question, as an investigator, you basically will have access to all the pathways, and you can see more or less where, like, the entire container on which pathways can be taken. You wouldn't know which pathway will be taken, but you will have access to all of the artifacts, you will have access to all the strings, all the user agents. Am I correct?
Yeah, but that's the thing, so the neural network, in order to execute, is going to take an input. What that input depends. It can be a user agent, as you mentioned, and that's going to go through a path, or it can be something else. The thing is, like, if you're going to give it the wrong user agent, it's not going to execute, or it's going to say something gibberish. So you can target specific user agents. But for me as an investigator, if somebody tells me, please check that out, and I have no idea from where to start, I will not start. Or you can actually, if you train your neural network hard enough, and that's enough, it's actually possible for it to learn JavaScript, which is not necessarily a good thing. And when I put a wrong input, it's actually going to take me on a branch that doesn't exist. And who knows exactly what's going to happen there. But it's complicating my life as an investigator because I have no vision on what's the next step.
Thank you.
Thank you very much. We had some questions here, if you still have them. No one? Okay, then we'll be going to the front row.
Oh, there is somebody there.
Or someone.
There's somebody in the back.
Who's closer to you, maybe? Yeah, thank you. We'll be getting in the front row as well, okay?
Do you measure or do you have some metrics about the performance of using machine learning algorithm in JavaScript?
What do you mean by that? Performance
I
on?
expect to not be feasible, to do not be able to do it in production, by example, because of the performance.
Oh, no, don't worry. I mean, it's really fast. And it can learn really large patterns. I mean, we actually generated like 20K code with a single model, 200 cells. So it's really fast. I mean,
Yeah, plus take into consideration, like, there is one big project, and it actually was the last in our list, like TensorFlow, so that's Google-owned project, and they're investing a lot in machine learning in JavaScript. So I presume they have the solution for computational issues.
Okay, thank you.
We'll be coming to the first row. If you still have the question, it's still there. You're very determined. Yeah, just tiny little second. Until we have a teleportation technology, we'll just walk.
I wanted to ask you what's next, and if you plan to use the machine learning for defensive mechanisms.
So that's two questions. Yes, the last thing I mentioned was the example when we train a neural network on different user agents and see how it behaves there. And we want to go with that further. And also the malware part. Like, we want to build a piece of, not necessarily malware, because I'm not such a great programmer there, but I want to actually build a binary that has machine learning capabilities and neural network inside, and try to make it as I explained, and then to debug it to see exactly how I can see the code there, what I'm going to see, if it's possible for me to actually understand and gather IOCs from it. And for the second thing, we actually do have a couple of projects that are defensive. We just released one project that has a patent, and it's basically detecting anomalies in command line. And we're actually going to discuss about this at the conference in 2 weeks at this site in Bucharest. Thank you.
We'll be taking one last question, if there's any. If not, we'll be closing. So maybe you have some questions or things that you would like to discuss in private, and we will invite you to talk with our guests in private afterwards. Thank you very much.
Thank you.